Hello, and welcome to this presentation related to first order differential equations of the form dy by dx is equal to a function of x function of y. This presentation builds on previous presentations and considers further problems associated with this form of first order differential equation. It's important to note that there are previous presentations related to this type of differential equation. First presentation relates to the solution of first order differential equations having the form dy by dx equals the function of x. Second presentation, we solve equations of the form dy by dx equals the function of y. And a third presentation solves problems of the form dy by dx equals a function of x function of y. And as I say, this current presentation considers further problems associated with this type of first order differential equation. It is strongly encouraged that you've reviewed the previous presentation before reviewing the contents of this presentation, as it contains much underpinning knowledge required. Here's a presentation overview. Initially, we outline all the questions considered within the presentation. That means we will review all the questions very briefly, and we will state the approximate start times should you want to move directly to the solution of a particular question. I have within each question tried to label the solutions to show you all the steps that I'm using to develop the solution. In your solutions you may have less steps, you may have different, even preferable solutions to that I'm presenting, but my solutions are aimed at helping technician engineers start these problems, as from my experience technician students find these questions very difficult. Then we do have a brief recap of the previous presentation. This is essentially extracts from the previous presentation. We state standard integral tables, standard differential tables, the laws of logs, the laws and the rules of indices, etc. And there is a worked example again extracted from the previous presentation. Then we have the essence of the presentation, which is the worked solutions to all the questions. As I said, these are quite detailed solutions, and I do in some instances provide alternative solutions to some of the questions. This essentially relates to the fact that all solutions involve using integration, but where appropriate I try to use standard integrals, and particularly this standard integral, as it can be very useful for solving certain problems. And I sometimes show the same question, but this time solved applying integration using substitution. There is a separate presentation related to integration using substitution. And here are the approximate start times related to these three sections. Please note for your reference that all times are rounded to the nearest minute. So here are the first few questions related to differential equations of the form dy by dx is equal to a function of x function of y. So we have questions 30 to 32 on this slide. Question 30, here's the equation dy by dx is equal to 2y multiplied by x squared. Notice that all answers are shown on the right hand side in square brackets. And question 30 actually has two solutions, and I'll work through both of the solutions within the presentation. Question 31, dy by dx is equal to y cos x, and question 32, x plus 2 in the bracket multiplied by dy by dx is equal to 1 minus y. Again, the answers are shown in the square brackets on the right hand side. Note solutions to these questions involve a constant of integration. In fact, question 32 is shown in terms of the constant of integration. So these are classified as general solutions. These can all be solved by rearranging the x terms onto one side of the equation, the y terms on the other, and then integrating both sides of the equation. Full work solutions are shown to all the questions for you to review at your own pace. Obviously, the solutions shown will be my attempts at these questions, but I'm not saying these are definitive solutions. You may find your own, possibly preferable solutions to that I'm showing. And here are the approximate start times related to questions 30, 31 and 32. Please note all times are rounded to the nearest minute. Questions continued here, question 33 through to 36. So for question 33, dy by dx is equal to, in a bracket, 2x squared minus 1. And that's all divided by a second bracket here of 3y plus 2. I'm writing all these equations using one-line formatting, so that doesn't confuse you. It's a more concise way of writing the equation, but can be sometimes more difficult to understand. But basically this first bracket is the numerator, the top line on the right hand side, and this bracket here is the denominator, the bottom line on the right hand side. And note within question 33, as indeed within all the questions on this slide, we're actually given an initial condition of x is equal to 0, y is equal to 0. So that will allow us to find a particular solution. So notice in the answer in the square bracket here, there is no constant of integration c. We've been able to evaluate the constant of integration because we're given the initial condition. And that's the same for all of the questions. Question 34, dy by dx is equal to the exponential function raised to the power of x minus 2y, and again we have initial condition, so in our final answer shown here there is no constant of integration. Question 35, half multiplied by dy by dx is equal to e to the power of x plus 3y. We're given the initial condition, so our final answer has no constant integration. In question 36, we have y multiplied by in the bracket 1 plus x plus x multiplied by in the bracket 1 minus y multiplied by dy by dx is equal to 0. We're given the initial condition that x is equal to 1 and y is equal to 1. Answer again shown in the square bracket. All these answers relate to the particular solution for each question. And here are the approximate start times related to question 33 through to 36. Questions continued. The slide shows questions 37 to 39. These are expressed slightly differently in that they state to show that or prove that a given solution is correct. So in question 37, it states show that the solution of the differential equation, stated here, is of the form y is equal to the square root of, in our curly bracket, a half multiplied by, in this second bracket, x to the power of 4 multiplied by k minus 1, where k is a constant. So essentially we are given the answer in the question this time, and we have to show that is indeed the correct solution. Questions 38, again, they show that the solution of the differential equation, shown here, is of the form square root of the left-hand side bracket is equal to a constant. So we need to show that this left-hand side is indeed equal to the constant on the right-hand side in this particular case. Just notice the notation used here. Our initial expression here of y squared plus 2 in a bracket is effectively divided by the x squared plus 2. Note the -1 notation shown here. The reciprocal index used means divide by in this case. And for further clarity, here's question 38, showing the initial one-line formatting stated in the question, now written on 2 lines, shown here. So that's shown as 2-line formatting. And again, from the original question, 1-line formatting shown here, which is the answer, shown as 2-line formatting here. So I hope that helps with the understanding of the way question 38 is presented. And as I say, I will be using 1-line or single-line formatting throughout most of the presentation. And if you're using spreadsheet packages such as Excel, then often you have to insert the equation using 1-line formatting. And question 39, this time we're asked to prove that y is equal to x is a solution of the equation stated here, given the initial condition that x is equal to 1 and y is equal to 1. We have to prove that y is equal to x. So in question 39, we'll be able to derive a particular solution. There's no constant in the final solution. Whereas in question 37 and 38, these are general solutions, so they will contain a constant of integration. Whereas in question 37 and 38, these are general solutions. We will have a constant within our solutions. And here are the approximate start times related to questions 37, 38 and 39. Again, all times are rounded to the nearest minute. Questions continued of question 40 through to 42. Question 40, to solve the equation x times y is equal to 1 plus x squared times dy by dx. I'm going to solve for y. Answer shown on the right hand side. K is a constant here. Question 41. We've got to find the curve which satisfies the equation 2xy multiplied by dy by dx is equal to x squared plus 1, and that passes through the point 1, 2. That's x is 1, y is 2. So this will be a particular solution. There is no constant of integration in the final answer. And question 42. Solve the equation y multiplied by cos squared x multiplied by dy by dx is equal to tan x plus 2. And again, we're given the initial conditions, so there's no constant integration in the final answer. Notice when it says x is equal to pi upon 4, because we're involved with trig functions here, that means we must use radians. So pi upon 4 kind of gives that away as an angle. And here are the approximate start times related to questions 40, 41 and 42. Questions continued. Questions 43 and 44 are descriptive questions. Basically the same approach to solution as per all the previous questions, but we have to extract the information from the question. So question 43, a capacitor, you'll see, is charged by applying a steady voltage, symbol capital E here, to a resistance, capital R. The potential difference between the plates, capital V, is given by the differential equation C multiplied by R multiplied by dV dt plus V is equal to E. We've got to solve the equation for V, and we're given here that V is equal to 0 and T is equal to 0. And also once we found our solution, we then have to evaluate V, given that is E is equal to 20 volts, C is equal to 25 microfarads, R is equal to 300 kiloohms, and time T is equal to 2 seconds. Be careful of the prefixes here. We have a micro prefix and a kilo prefix, so you need to account for those in the calculations. So there are two answers in the square bracket here. Here's the solution to the problem, and this is the evaluation exercise using the solution to find the final voltage. So question 43 was electrical context, question 44 is a thermodynamic context. We've got to find the adiabatic expansion of a gas, and given the formula Cp multiplied by dVV plus Cv multiplied by dP by P is equal to 0. We're informed that Cp and Cv are constants, so we've got to show that Pv to the n is a constant, where n is equal to Cp divided by Cv. And here are the approximate start times related to question 43 and question 44. I will show a few brief extracts from the previous presentation, purely for reference here. One of the problems with solving this type of differential equation is it requires lots of underpinning knowledge. For example, we sometimes require the use of integration using substitution, also to be able to differentiate using standard forms. You need to be able to apply the laws of logarithms, the laws and the rules of indices, and also be aware of our trigonometric functions, sine, cos and tan, and be aware of their reciprocal functions, cosecant, secant and cotangent. And this is the major contribution to the complexity of these particular type of problems. There are three types of this first order differential equation. In this presentation we're considering the dy by dx as a function of x, function of y, and all of these problems can be solved using the integration process. But in each case it will be possible to separate the y terms onto one side of the equation and the x terms onto the other. Solving these types of differential equations using direct integration is termed separating the variables. Now, further reference information shown on this slide, we have the laws of logarithms, we have the laws and the rules of indices, and we have trigonometric ratios outlined here. Further reference information, referring to this throughout the presentation. This is a standard integral table, contains extracts from previous presentations. The table just includes integrands that are used within the presentation. Just for clarity, some students are slightly confused by the formatting shown in the table, where it shows, for example, 1 upon a multiplied by the sine of ax plus the constant integration c. That could actually be written as sine ax divided by a. So multiplying by 1 upon a is the same as dividing by a. As I say, sometimes students find the fractional notation confusing, but again, the same with the cos function here. It's negative 1 upon a multiplied by the cos of ax. That's the same as negative cos ax divided by a. And the exponential function here, 1 upon a multiplied by e to the ax, is the same as e to the ax divided by a. So I've just added those illustrations in for clarity, that's all. Reference information again, so a table of standard derivatives this time. Again, a further extract from a previous presentation, just outlining how this type of equation, where we have dy by dx is equal to a function of x multiplied by a function of y, we will be able to separate the variables and have all the y terms onto one side of the equation and all the x terms on the other. And we solve this problem by integration, integrating both sides as shown here. Again, an extract from a previous presentation. This was example 3. We worked through in detail in the previous presentation. I'm just going to highlight salient parts of the solution here. So again, given a question, we need to rearrange for x terms on one side of the equation, y terms on the other. Doesn't matter which side they're on, as long as we have the distinctive variables on each side of the equation. So you can see that it's been rearranged here, so all the y terms are on the left hand side, all the x terms on the right hand side. That will allow us to integrate, in this case, the left hand side with respect to y, the right hand side with respect to x. And where appropriate, we use standard forms in our table. For the x, in this case, we can use item 2 in this table here to integrate the right hand side, shown here. And there are actually two ways of solving the left hand side integral. There is a standard form for this integral, shown here in the table, where if the numerator is the first differential of the denominator, we can use this solution from our standard integral tables. It does need slight manipulation to use this formatting, but if you understand how to rearrange into standard form, it's a very quick solution. Alternatively, we consider the left-hand integral solved using the process of integration by substitution. Either method we use will produce the same answer. Again, we covered these techniques in the previous presentation. Example 3 continued here. And one of the aspects that students find most difficult with this type of problem is after the integration process, rearranging the equation into the final solution given. Because often that involves you applying the laws of logarithms or the laws and the rules of indices, sometimes exponential functions and transposition. So sometimes the latter part of the questions are actually where the most problem occurs. But overall, these are very difficult problems. So the essence of the presentation now is to work through a whole raft of questions. Over 10 questions are considered in this presentation, and I've tried to labour the solutions to show most of the steps involved within the process to get the final solution. So essentially I would just show you these solutions and let you review them at your own pace. Here's question 30, stated here. And notice in this particular question, we're actually given two general solutions to solve for. I'll outline both solutions on the following slides. So here's question 30. We're given the equation dy by dx is equal to 2y multiplied by x squared. We don't really need the brackets on the right hand side there. So I'll just briefly outline this solution. It's a general solution. We will end up with a constant integration in the final answer. So given dy by dx is equal to 2y multiplied by x squared. So rearranging is quite straightforward here. I multiply both sides by dx and divide both sides by y. I'll have dy divided by y on the left hand side. On the right hand side I have 2x squared multiplied by dx. You might consider why not divide by 2y and not y. Well, I'll show you that alternative solution later on. So on the next line we're simply going to integrate. Notice I brought the y from the bottom line here to the top line, so I've stated it's y to the -1 multiplied by dy. On the right hand side I've I've left the constant 2 outside of the integral, so it's 2 multiplied by the integral of f squared dx. So on the left hand side, integrating y to -1 equals ln y, and on the right hand side we're integrating the x squared respect to x, so that's of the form ax to the n is equal to ax to the n plus 1 over n plus 1. So referring back to our standard integral tables here, this is the solution for the left hand integral, and this is the solution for the right hand integral. Standard forms. All I've done on the next line is now to rearrange the equation. So I divided both sides by 2, by half. Remember, when you divide by 2, you divide throughout by 2, so the ln y is divided by 2, the 2x cubed divided by 3 is divided by 2, so we end up with this answer here. But also the constant of integration is divided by 2. So on the next line, I've simply made the lowercase c constant of integration an uppercase c, another constant if you like. So lowercase c divided by 2 is equal to uppercase c. So that's how I write my solution with the uppercase c at the end of the equation. That confuses some students, but just try and think of it that lowercase c divided by 2 is a constant. So I can just call that another constant, call it uppercase c in this case. So that's the general solution to question 30. Here's question 30 solution. The thing that's different about this solution is when I rearrange the equations, I actually divide both sides by 2y here, so I have dy divided by 2y is equal to x squared multiplied by dx. That's shown two-line formatting here, but we've ended up with the same final solution. Here's question 30, our alternative solution, just outlined in greater detail here, using one-line formatting. Here's question 31. Y by dx is equal to y multiplied by cos x. And here's the general solution we need to find. The full root solution is shown on the following slides. Question 31. Given the equation dy by dx is equal to y cos x. So again, we can rearrange the equation to get the y terms on the left hand side and the x terms on the right. So divide both sides by y. On the left hand side we have dy divided by y. And then multiply both sides by dx. On the right hand side we have cos x multiplied by dx. Again, these are both standard integrals. On the left hand side we have the integral of y to -1 dy. Put the y to the top line on the left hand side. On the right hand side, standard integral of cos x respect to x. So again, referring to our standard tables, here's the integral for the left hand side and the integral to the right hand side. So the solution is ln y is equal to sin x plus c. Again, a general solution. Here's question 32. X plus 2, bracket multiplied by dy by dx is equal to 1 minus y. The solution is shown here in the square bracket, and notice it's stated as constant c is equal to the ln function. The full root solution is shown on the following slides. Question 32 solution. We're given the equation of x plus 2 in the bracket multiplied by dy by dx is equal to 1 minus y. Again, we're going to rearrange the equation to divide both sides by 1 minus y. We have dy divided by 1 minus y. Then multiply both sides by dx and divide both sides by x plus 2. On the right hand side we have dx divided by x plus 2 in the bracket. Now both sides are actually standard form, and they're of the same standard form. Referring to our standard integral tables, it will be this standard form shown here, where if the numerator is the first differential of the denominator, we can simply write the solution down as ln function of x plus c. So thinking through on the right hand side here, if we differentiate the denominator of x plus 2, and differentiating here, the x becomes 1 and the 2 will disappear. So the denominator would be 1 and the numerator is 1. So the numerator is the first differential of the denominator. So it integrates to ln of x plus 2. On the left hand side, we can apply the same process here. If we differentiate the denominator, the 1 minus y, we will end up with the 1 will disappear and the minus y will become a minus 1. But on the top of the equation, we effectively have a 1 times dy. But differentiating denominator is negative 1. So to make the standard form work, we have to place a negative 1 in the numerator of the integral. But because we're multiplying the top line by negative 1, it means we also have to divide the bottom line by negative 1. So I have this fraction of 1 divided by negative 1 outside of the integral to effectively cancel the negative. So the integral becomes negative 1 divided by 1 minus y. When we differentiate 1 minus y, we get negative 1. So our solution then holds for the function of x. And don't forget 1 divided by negative 1, of course, is negative 1. So we'll just simplify that on the next line. Question 32, solution continued. I've tried to show on this slide, hopefully with more clarity, how we use this standard integral shown here. Just repeated the integrals from the previous slide, but using two-line formatting. So on the left-hand side, we're integrating 1 dy divided by 1 minus y. And on the right-hand side, we're integrating 1 dx divided by x plus 2. So if we now consider the left-hand side, and we're differentiating, note the standard integral states that the numerator is the first differential of the denominator, so we're differentiating. So referring to our standard differential table, we're using the ax/n function. We've reviewed standard differentiation in previous presentations, so I'm assuming you're familiar with the process here. So when we differentiate the 1 minus y with respect to y, the 1 will disappear and the minus y becomes minus 1. When we differentiate x plus 2 with respect to x using the same standard form, the x will become 1 and the plus 2 will disappear. So dy by dx of x plus 2 is 1. Question 32, solution continued. Just repeated this line from the previous slide related to the left-hand side differential and the right-hand side differential. So what we know in this case, we need to apply a negative 1 factor to the left-hand side when integrating with the standard form function dash x divided by function of x, this standard form shown here. So for the right-hand integral, when we differentiate the denominator x plus 2, we have the value of 1, and we have 1 in the numerator. So we comply with our standard form here. So we can simply write the solution for the right-hand integral as ln of the function of x in the denominator x plus 2. I've added the constant integration on the right-hand side here. However, for the left-hand integral, when I differentiate the denominator of 1 minus y, we can see we have negative 1. So to comply with our standard form, I must have a negative 1 on the top line. However, because I'm actually changing the sign of the integral, I need to counteract that negative 1 by placing a negative 1 in the denominator outside of the integral. I have 1 upon negative 1. Notice I've just stated the negative 1 here, because obviously 1 divided by negative 1 in this case is negative 1. So I can simply write my solution down as ln of the denominator 1 minus y, but of course I have my negative 1 outside factoring up the log function. So it's negative ln 1 minus y. So that's how we use the standard integral form shown here. And in this case, it saves us having to apply integration using substitution, which is a slightly more lengthy process. To integrate on the left-hand side, we get ln of 1 minus y plus c. So that simplifies to this line here. And because the answer is shown in terms of constant c, we just simply need to rearrange the equation. So I've added the ln of 1 minus y to both sides of the equation. And using the first law of logarithms, adding the logs is like multiplying the brackets. So our final solution for c is shown here. If you're slightly confused with the integration process shown here, I would encourage you to refer to the previous presentation where we consider this in a bit more detail. Question 32 is an alternative solution. Within this solution, we're going to apply integration using substitution. So as per the previous solution, we have the same integrals to solve, integrating respect to y on the left-hand side and integrating respect to x on the right-hand side. But with this solution, we need to make a substitution. So on the left-hand side, we've let u equals to 1 minus y. On the right hand side we let v is equal to x plus 2. So now we differentiate u with respect to y, and we find that dy is equal to negative du. On the right hand side here we differentiate v with respect to x, and we find that dx is equal to dv. So on the left hand side we have the integral of du divided by u, negative outside the integral here. On the right hand side we simply have the integral of dv divided by v. These are both standard forms, so ultimately we have the same expression here for c as we had in our previous solution. I just called the constant c1. Just note in this solution the final constant c1 is actually equal to negative c. That occurs because I actually placed the constant integration initially on the right hand side of the equation. So when I rearrange the equation to make all the log terms positive, I actually had a negative c, which I renamed as a positive constant c1. Here's question 33. dy by dx is equal to 2x squared minus 1 divided by 3y plus 2, and we're given an initial condition that x is equal to 0, y is equal to 0. Here's the solution we're trying to obtain. I encourage you to start the presentation, attempt question 33, by the full work solution shown on the following slides. Question 33. This is going to be a particular solution because we're given the initial condition shown here. So from dy by dx is equal to 2x squared minus 1 divided by 3y plus 2. We simply rearrange, multiplying both sides by 3y plus 2. We have 3y plus 2 multiplied by dy. Notice I need the bracket here to ensure my BODMAS is correct. And multiplying both sides by dx, we have 2x squared minus 1 in our bracket again, multiplied by dx. These are both standard integrals here. Back to our integral table. Both left and right hand side of the equation of this form here. So integrating the left hand side, shown here, integrating the right hand side, I'll put my constant integration on the right hand side. It doesn't matter which side you place the constant integration. Here we're given an initial condition when x is equal to 0, y is equal to 0. So I simply put the value for y, in this case on the left hand side, values for x on the right hand side, of course they're the same here. So constant c is 0 in this case. So here's our particular solution. And I've just slightly reformatted that on the final line. 3 divided by 2, of course, is 1.5. So that's the solution to question 33, a particular solution, because we were given an initial condition in the question. Question 34, dy by dx is equal to e to the power of x minus 2y, and we're given that x is equal to y is equal to 0. Here's the solution we have to determine. The full work solution is shown on the following slides. Question 34, again, we have to find a particular solution because we're given x equals to y is equal to 0. So dy by dx is equal to e to the power of x minus 2y. On the right hand side I'm going to apply the first law of indices so I can write the exponentials in terms of e to the x, in this case e to the negative 2y. And note I'm applying now the reciprocal rule of indices. E to the negative 2y means reciprocal, so on the right hand side I have e to the x divided by e to the positive 2y, and then rearranging I multiply both sides by e to the 2y, so my left hand side I multiply both sides by dx, so the right hand side of the equation. Both standard integrals here, referring to our integral table. This is the standard form we'll be using, shown on 2 lines here for reference. So left hand side integrating e to the 2y respect to y becomes e to the 2y divided by 2. And on the right hand side integrating e to the x respect to x becomes e to the x, and I put the plus c on the right hand side. So that's the general solution, but of course in this case we're given the initial condition, so we need to now apply that to find the particular solution. So question 34, solution continued here. So given the initial condition, x is equal to 0, y is equal to 0, we insert these into our equation from the previous slide. Note that of course e to the 2 times 0 would be e to the 0, which has a value of 1. And the same on the right hand side, e to the 0 and evaluated becomes 1. To have a half on the left hand side is equal to 1 plus c on the right hand side. Rearrange it for constant c, it's negative a half. So we can write our solution down now as e to the 2y divided by 2 is equal to e to the x minus a half. Or if you multiply both sides by 2, we can write the solution as e to 2y is equal to 2e to the x minus 1. Remember, we're multiplying throughout by 2 here. So that's the final solution for question 34. Question 35, for a half multiplied by dy by dx is equal to e to the x plus 3y, and we're given that x is equal to y is equal to 0. Solution shown here. The full work solution is shown on the following slides. Question 35, for the half multiplied by dy by dx is equal to e to the x plus 3y, given the initial condition here. I'm going to let you review this solution at your own pace. It's very similar to that we reviewed in the previous question. Again, we're using the same standard integral on both sides of the equation. And question 35, solution continued. Imposing the initial conditions, we find our particular solution. And again, I'll let you review this slide at your own pace. Here's the final answer. Question 36, stated here, we're given x equals to y is equal to 1. Here's the solution, and this is outlined in full on the following slides. Question 36, we're given y multiplied by 1 plus x multiplied by 1 minus y in the brackets multiplied by dy by dx is equal to 0. And also we have a initial condition when x is equal to 1, y is equal to 1. So again, we need to rearrange the equation, having all the x terms onto one side of the equations, the y terms on the other. I tried to be very detailed with the steps here, so I'm going to let you review this at your own pace. Because ultimately we end up with the two integrals, in this case x is on the left hand side and y is on the right hand side. The standard forms of integral we use here is the ax to the n format and also the x to the negative 1 format shown here. We need both of those here on the left hand side and the right hand side. I'll let you review this slide at your own pace, perform our general solution of the constant integration c here. And question 36, solution continued. Now impose the boundary conditions, x is equal to 1, y is equal to 1, the constant of integration equals to 0, and rearranging the equation and using the first law of logarithms, we show our final solution. Question 37. In this case, we're asked to show that the solution of the differential equation here is of the form stated here, noting that lowercase k is a constant. The full work solution is shown on the following slides. Question 37. We're given this differential equation and we have to show that the solution is in this format shown here. As always, with this type of question, we'll be able to rearrange the x terms onto one side and the y terms on the other. So given the initial equation, on the next line I've multiplied throughout by dx, and on the next line I've divided throughout by 1 plus 2y squared in the bracket, and divided throughout by x. So now I have all my y terms on the left hand side and all my x terms on the right hand side. So next we form our integrals, both standard form. On the right hand side I've simply brought the x to the top line here, so we have the integral of x to the negative 1 respect to x, and that's a standard form in our tables. And on the left hand side we can actually make this into standard form using our function dash x divided by function of x integral. If we differentiate the denominator, we would end up with 4y. At the moment on the top line we actually have 1y. So if I was to factor the numerator by 4, shown here on the next line, then when I differentiate the denominator I do obtain the numerator. But of course, for counteracting the factoring of the numerator by 4, I effectively have 1 upon 4 outside, a quarter outside, so that I do not affect the overall question we're trying to solve. But this essentially then makes the left hand side into standard form. Question 37, solution continued. So considering the integration of the left-hand side, we have y divided by 1 plus 2y squared, integrated with respect to y. Now if we differentiate the denominator of the left-hand side, we have 4y, but currently in the numerator of the integral we have just 1y. So in this case, we need to apply a factor of 4 to the left-hand side numerator when integrating with the standard form function dash x divided by function of x. So now the integral becomes 4y divided by 1 plus 2y squared, integrated with respect to y. So now we comply with the standard form. The numerator is the first differential of the denominator. But to ensure we do not actually change the question being asked, we have to apply the 1 upon 4 factor outside of the integral. So the solution to the left-hand integral is ln of 1 plus 2y squared, but of course that's factored by a quarter. The right-hand integral is simply standard form, solution directly read from our table. So referring to our standard integral table, these are the two integrals we'll be using. I can integrate both sides then, ln of 1 plus 2y squared, but of course this is multiplied by the quarter factor here. On the right hand side I integrate x to negative 1, I have ln x. And instead of adding c this time, notice I've actually added ln c, and the reason for that is in the solution that we're trying to find, stated here in the question, there is no natural log term. So by stating ln c instead of purely c, you'll see I'll be able to eliminate the natural log functions from the expression. So on the next line I've simply applied the third law of logarithms to the left hand side. So on the left hand side I have the natural log of the bracket raised to the power of a quarter, that's the application of the third law, and I've applied the first law of logarithms to the right hand side. So adding ln x plus ln c can be written as ln of the x times c in the bracket. Question 37 of solution continued. Just repeated this line from the previous slide for convenience. So on the next line we effectively remove our logarithms by taking antinatural logs, sometimes referred to as exponentializing the equation. So now we have our bracket here raised to the power of a quarter is equal to xc on the right hand side. Then I've raised both sides to the power of 4, so here the quarter is removed. That's the third law of indices problem. xc has to be raised to the power of 4. The next three lines are rearranging for y. Last line here, we're simply letting constant k equal to c to the power of 4. So here's c to the power of 4, which is being replaced with lowercase k. So that's our final solution for question 37. Here's question 37, alternative solution. So as before, we commence with the rearrangement, y terms on the left-hand side, x terms on the right-hand side. But this time we're applying integration using substitution to solve the left-hand integral. So instead of integrating with respect to y, we integrate with respect to u, shown here. But our solution thereafter is similar to that of the previous solution. Question 37, alternative solution continued. I'll let you review the slide at your own pace, but we end up with exactly the same answer as in the previous solution. So it's essentially the integration process that was different with this solution. Question 38, again we have to show that the solution to the differential equation, shown here, is of this form. The constant is equal to this expression here. The full work solution is shown on the following slides. Here's question 38, commencement of the solution. We're given in the question y squared plus 2 multiplied by x squared plus 2 raised to the power of negative 1 is equal to x and negative 1 multiplied by y multiplied by dy dx. Rearranging the equation here on the next line, I've multiplied by dx, and multiplied throughout by x. On the next line I've divided throughout by y squared plus 2. So I now have y multiplied by dy divided by y squared plus 2. On the left hand side here, slightly rearranging of x multiplied by x squared plus 2 raised to the power of negative 1. That's multiplied by dx. So again, all the x terms on one side, all the y terms on the other. just slightly rearrange the right hand side here using the negative index for the bracket. On the next line we integrate the left hand side, integrate the right hand side. Again we need to try and make them into standard form. At the moment if we differentiate the denominator, the x squared plus 2, that differentiates to 2x. So it's not standard form because at the moment we have 1x on the top line, the x squared plus the 2 to negative 1's on the bottom line. So we need to multiply the numerator by 2, but that means we have to have a half outside of the integral. Now we've made it into standard form on the left hand side and a similar approach on the right hand side. So again, this is the standard form we're using to integrate both left hand side and right hand side. Question 38, solution continued. Here's a more detailed slide relating to the integration process using our standard form. Essentially, to make both integrals standard form, we have to factor the numerator by 2 and factor the integral by a half. But I'll let you review the solution at your own pace. Question 38, solution continued. Just repeating our integrals here from the previous slide. So on integrating, we have a half ln of x squared plus 2 on the left hand side, a half ln of y squared plus 2 on the right hand side, plus our constant of integration. On the next line we're simplifying, multiplying throughout by 2, so the half is removed on the left hand side. On the right hand side, half is removed against the ln function. But notice the constant c in the above line would have to be multiplied by 2. So what I'm doing on the next line is letting k is equal to 2c. So my constant of integration now becomes k. So 2c or k, they're both constants. But to simplify the expression, I'm just using k. On the next line, we simply rearrange for k. I'm subtracting the ln of y squared plus 2 from both sides of the equation. Next line, we apply the second law of logarithms to the left-hand side. So we're subtracting the log terms. So that's the same as log of the x squared plus 2 now divided by the y squared plus 2 term in brackets. Next, I've just applied the reciprocal rule of indices. Not really required here to do that, but that's what I've done here. The bracket that forms a general solution. But notice in the question we have to show that the constant is equal to this term. Note there's no log term in the expressions, so we need to remove the log term from our equation. So to remove the log term, we take exponentials of both sides of the equation. In other words, raise both sides to the base of e. So on the left hand side the ln function is removed, but on the right hand side the constant is now an exponential form. It's e to the power of k. Again, because we have to show a square root in our expression given in the question. So I square root both sides on the next line, the square root in here, and square root in the constant. But note the square root of e to the k is just another constant. Could give it another label if we wanted to. But on the last line I've simply written the constant in the format of x squared plus 2 all raised to the power of a half, that's square root, don't forget, divided by y squared plus 2 all raised to the power of a half. And that's essentially what we've been given in the original question. It's just they've used a negative index for the y squared plus 2 bracket. So that completes the solution for question 38. Question 38, an alternative approach to the solution. Again, these are my handwritten notes, so apologies for the quality. I commence a solution from a slightly different initial problem, but essentially we rearrange the equation to get all the y terms on the left hand side and the x terms on the right hand side. And of course we have to integrate both sides to develop our solution, but this time we've used integration using substitution. A substitution here for the left hand side, a substitution here for the right hand side. Again, I'll let you review the solution at your own pace. Question 38, alternative solution, continued. So we can cancel our terms here, y with y, and here x with x. Then we integrate both sides, so left hand side integrate u to the negative 1 respect to u, right hand side integrate v to the negative 1 respect to v. From the standard integral tables, The left-hand side integrates to ln u, the right-hand side to ln v. And notice I've added my constant of integration here on the left-hand side, call it C1. Doesn't matter really which side you add the constant integration, but in this case, to attain the solution required, I've added the C1 to the left-hand side. Next line, I simply rearrange for C1, so I've subtracted ln u from both sides, and on the next line, C1 now equals to the natural log of v divided by u. That's the second law of logs applied here. On the next slide, I simply exponentialize both sides of the equation, in other words, taking natural logs of both sides of the equation. C2 on the left-hand side, which is equal to v divided by u. Then I've square rooted both sides, so I have the square root of C2, which I've now called constant C, and on the right-hand side, the square root of v divided by u. And finally, back substituting for u and v, I have my final solution for c. It's the square root of x squared plus 2 divided by y squared plus 2. And that's essentially the same expression for c we found in our previous solution. Shown here in a slightly different format, that's all. Question 39 has to prove that y is equal to x is a solution of the equation stated here when x is equal to 1 and y is equal to 1. Full work solution shown on the following slides. Here's question 39, commencement of the solution. So in this question we're asked to prove that y is equal to x given the equation shown here. And we're also given the initial condition when x is equal to 1, y is equal to 1. So we'll be able to find the constant integration this time. I'll let you review the solution down to here. It's all basically algebraic manipulation. Get the x terms on the left hand side and the y terms on the right hand side. And at the bottom of the slide here we form the integrals shown here. Question 39, solution continued. Just repeated our integrals here for convenience. These are actually standard form. Referring back to our standard integral table, we could use this integral shown here. But on this particular case, I thought I would try substitution, just to be different really, show you a different method. We need to apply substitution to the left-hand side and the right-hand side. When you look at the expressions, they're actually very similar. So obviously the same approach to the integrations required both sides. I'll let you review the integration process at your own pace. We have covered integration using substitution in a previous presentation. Notice the integration using substitution requires some differentiation as well. Here's our standard derivative table, standard differentials we'll be using. And question 39, solution continued. We impose the initial condition given here, and then x is equal to 1, y is equal to 1, inserting for x, value of 1, inserting for y, the value of 1. But it's clear to see that the constant will be 0. Again, I think it's clear to see at this stage that x equals to y. That's what the final solution states. Question 40 has to solve the equation stated here for y and the solution stated here. This general solution is fully worked on the following slides. Here's question 40, commencement of the solution. We have to solve the equation x multiplied by y is equal to 1 plus x squared, in our bracket here, multiplied by dy by dx. We're solving the equation for y. I'll let you review this solution at your own pace. Again, we can form a standard integral on the left hand side and the right hand side of the equation. These are the standard forms we'll be using. And question 40, solution continued. Here's our final solution for y. Note that k is the constant in this case. Question 41. We have to find the curve which satisfies the equation stated here and which passes through the point stated xy here 1, 2. Slightly different wording in this question to previous questions, but the overall approach used to find a solution is very similar to that of the previous questions. Here's the final solution to the question, which is fully worked on the following slides. Here's question 41, commencement of the solution, given the equation in the question, and given the boundary condition. Questions worded slightly differently than previous questions, but essentially the solution sequence is the same. In this case, we have standard integrals on both sides of the equation. These are the standard solutions we'll be using. Solution 1 on both sides of the equation and solution 2 on the right hand side of the equation. And question 41, solution continued. We have our initial condition given, so we put the y on the left hand side of the equation and the x on the right hand side. Constant of integration, c is 3.5. And here's the final solution. We're asked to produce 2y squared is equal to x squared plus 2 multiplied by ln x plus 7. Here's question 41, alternative solution. Apologies again, this is a handwritten solution. And we commence with the equation given in the question. And as always, rearranging to have the y terms on one side of the equation, the left hand side in this case, and the x terms on the other. I will let you review the solution at your own pace. And question 41, alternative solution continued. Here we impose the initial condition given in the question. Again, I'll let you review the solution at your own pace, but our final solution is shown here. Question 42, asked to solve the equation, stated here, given the initial condition of y is equal to 2 when x is equal to pi upon 4. Solution defined, stated here. Again, the solution is fully worked on the following slides. Question 42, commencement of the solution. Slightly different functions to deal with here. We're asked to solve the equation y times cos squared x times dy by dx is equal to tan x plus 2. And we're given the condition that when y is equal to 2, x is equal to pi upon 4. That instantly suggests we'll be using radians in our solution. So again, the equation can be arranged for the y terms on one side of the equation and the x terms on the other. So we start off with the expression as given in the question, and we can rearrange it so we have y terms on the left hand side and all the x terms on the right hand side. Notice we're dividing by cos squared x here. Integrating the left hand side will be a standard form. So here's our standard integral for the left hand side of our equation. But for the right hand side we will need to integrate using substitution. Our substitution in this case, u is equal to tan x plus 2. From our standard derivative table, differentiating tan ax becomes a sec squared ax. But notice the a in our case is actually 1, so differentiating tan x become sec squared x. So next line we have du dx is equal to sec squared x. Differentiating the constant 2 of course disappears in our standard forms. We can rearrange for dx, since du is divided by sec squared x. And remember from our standard trigonometric tables, sec squared x is 1 upon cos squared x. So in this case, dx is equal to cos squared x du. So referring back to our reference information, we know that sec theta is 1 upon cos theta. In other words, sec theta is the reciprocal of cos theta. So sec squared theta will equal 1 upon cos squared theta. That's essentially what we're using here to rearrange our equation. This is our integral here. So what we find when we use our substitution of u and replace in our dx, the cos squared x in the top line cancels with the cos squared x in the bottom line. Question 42, solution continued. This line repeated for convenience. So now both sides of the equation have standard integrals of the form ax to the n. So left hand side integrates to y squared divided by 2, right hand side to u squared divided by 2 plus the constant integration, and we just back substitute for u, so we have tan x plus 2 all squared divided by 2. On next line I simply multiplied throughout by 2, so y squared on left hand side, have tan x plus 2 all squared plus 2 times the constant of integration. Question 42, solution continued. So we have our general solution, and we can impose our initial condition, x is equal to pi upon 4, y is equal to 2. So imposing the 2 on the left hand side, pi upon 4 on the right hand side. We can evaluate the constant c, it's negative 2.5 here. Just note we should be using radians in the solution. In other words, the calculator is set to radians mode. Pi upon 4 is in radians here. And question 42, solution continued. I'll let you review this at your own pace. It's essentially algebraic manipulation here to find the final answer, which is expressed in terms of y squared here. Question 43, a descriptive question. I'll let you read this at your own pace. Solution shown here. So a formula for v. We have to use the formula given some numerical values in the question. Full work solution shown on the following slides. So question 43, here's the commencement of the solution. This is actually a descriptive question here, so you need to read the question carefully. Slightly more confusing in the way it's presented, but essentially the solution is very similar to that we used in previous questions. So we're given a formula in the question, capacitance times resistance, and that's multiplied by dV by dt, rate of change of potential difference with time, plus V, and that's equal to a steady voltage labelled as E. So this time we do not have the variables of x and y. Our x in this case is actually t, and our y is actually capital V. So we need to rearrange the equation to begin with. So I've subtracted v from both sides of the equation. So on the next line I've divided both sides by e minus v, and I've divided both sides by CR. So left hand side dV divided by e minus v, on the right hand side dt divided by CR. Because CR is a constant, it could have remained on the left hand side of the equation, but I chose to divide by CR here. So now we have all the v terms on the left hand side and the t term on the right hand side. This is a standard integral on the left hand side. We've got the integral of, I've labelled it as 1 dV divided by e minus v, and on the right hand side integral of 1 dt divided by CR. So for the left hand side we can use the standard form f dash x divided by fx. On the right hand side simply the ax to the n format. So referring to our standard integral table, these are the two standard forms we'll be using for the left hand side and the right hand side. Notice when we differentiate the denominator on the left hand side, differentiate e minus v, that will actually become negative 1. So you can see I put a negative 1 in the top line, so I must have a negative outside of my integral here. On the right hand side I've just simply rewritten the equation with the CR to the negative 1 multiplying by the integral of 1 dt. So we do integrate. On the left hand side we get negative log e minus v. On the right hand side CR to negative 1 multiplied by t plus the constant integration I've labelled as k here. So that was using the standard forms to integrate. Question 43, solution continued. This is an alternative approach to the integration. This is integration using substitution. So if you don't want to use the standard form for the left hand side here, you can actually use substitution, but we'll end up with exactly the same answer for the left hand side of the equation. Right hand side of course the same also, just slightly rearranged. For the substitution method we do need to refer to our standard derivative tables, but we're just using the standard form ax to the n, anx to the n minus 1. So we end up with this standard form when we're using the integration by substitution method. Question 43, solution continued. So we're given the initial condition when v is equal to 0, t is equal to 0, so we can substitute the value of 0 for v here and 0 for t here. That produces constant k is equal to negative ln of e. So we have a solution here of negative ln e minus v is equal to t multiplied by cr to the negative 1 minus ln e. All that's happened on the next line, I simply rearrange the equation. So I've added ln e to both sides of the equation. I've then applied the second law of logarithms here because we're subtracting logs. So that's the same as ln of e divided by e minus v in its bracket. Taking anti-logs of both sides of the equation. The left-hand side is e divided by e minus v, or written here e multiplied by e minus v to the negative 1. And on the right-hand side we have the exponential raised to the power of t divided by cr, t multiplied by cr to negative 1. The next line we simply multiply throughout by the e minus v and the bracket there to produce this equation. Question 43, solution continued. I now need to rearrange the equation for v. So I've now expanded the bracket on the right hand side of the equation. I've added this term to both sides of the equation and subtracted e from both sides of the equation. Next I've divided throughout by this bracket here. Just brought the bracket to the top line and raised it to the power of negative 1. So eventually I have an expression for v, shown here, that I can use for the final part of the question, where it's given me some numerical values to essentially plug into the formula and calculate v. Question 43, solution continued. So here's our derived equation. We've got to use it to evaluate v, given the values here. They're all extracted from the question. E is equal to 20 volts, C is equal to 25 microfarads, R is equal to 300 kiloohms, and T is equal to 2 seconds. Just note, for convenience of the calculation, I've multiplied C by R here, which simplifies to 7.5. I simply insert the values into the above equation, and I find that V is equal to 4.681 volts. So that's a full work solution to question 43. Question 43, alternative solution, commences in a very similar way to the previous solution. We rearrange to have all our v terms on the left hand side and the t term on the right hand side of the equation. We use the process of integration using substitution here, so that u equals e minus v. Ultimately we end up with the integral on the left hand side shown here, and integral on the right hand side shown here. Integrals multiplied by 1 upon CR. I'll let you review the solution at your own pace. Question 43, alternative solution continued. We're now imposing the initial condition when v is equal to 0, t is equal to 0. So inserting the zeros appropriately within the equation, we find that constant c is equal to negative ln e. I'll let you review the rest of the solution at your own pace. It's basically algebraic manipulation. Just notice we're using the second law of logarithms on this last line here. And question 43, alternative solution continued. We ultimately end up with the final solution shown here. Again, you can review this at your own pace. And question 44. We're asked to find the adiabatic expansion of a gas, given this formula stated here, where Cp and Cv are constants. We're asked to show that P multiplied by V to the power of n is equal to a constant, and the exponent n is defined as Cp divided by Cv. The full work solution is shown on the following slides. And question 44, commencement of the solution. Again, quite a complicated question here. The context is the thermodynamic process. We're given in the question this equation. We have to solve this differential equation to show that Pv to the n is equal to a constant, noting that n is equal to Cp divided by Cv. So in this case the variables are v and p, so we need to rearrange to get v terms onto one side of the equation and p terms onto the other side of the equation. Standard integrals on both sides of the equation. I've just written the variables in terms of your reciprocal index on these lines. So from our standard tables, this is the integral we'll be using. So on the left hand side we get Cp multiplied by ln of v, right hand side we get negative Cv multiplied by ln p, plus the constant integration I've called that k here. I'll just slightly rearrange the equation on the final line, add in the Cv ln p to both sides of the equation. Question 44, solution continued. So next I apply the third law of logarithms on the left hand side. So I now have ln v to the power of Cp plus ln p to the power of Cv is equal to k. Applying the first law of logarithms now to the left hand side rather than the log terms. So that's the same as ln of v to the power of Cp multiplied by p to the power of Cv. And then taking anti-natural logarithms of both sides of the equation, exponentializing each side. The exponential cancel with the natural logarithm because they're inverse operations. On the right hand side we have e to the power of the constant k. So now I have a solution of v to the power of Cp multiplied by p to the power of Cv is equal to e to the power of k. Question 44, solution continued. Line repeated from the previous slide. We now raise both sides to the power of 1 divided by Cv, down here and here. We then apply the third law of indices to the left and right hand side of the equation. So we end up with v to the power of Cp divided by Cv and p to the power of 1. Think of applying the third law here. So for the v base you're multiplying Cp by 1 upon Cv, and for the p base you're multiplying Cv by 1 upon Cv, so it cancels to 1. And on the right hand side we get e to the power of k divided by Cv. The question states that n is equal to Cp divided by Cv, so we can write now v to the power of n multiplied by p is equal to e to the power of k divided by Cv. And if we let constant c equals to e to the power of k divided by Cv, which is a constant, then we end up with Pv to the n is equal to c. This is what we were asked to prove in the question. So again, a very complicated solution, question 44, but hopefully I've included enough steps to help you understand the way the solution unfolded. And here's the bibliography used to help generate this presentation, a very good engineering textbook for technician engineers. So I hope this presentation has been of some use to you, and as always, thank you for viewing.